Hi and welcome. In this video we are gonna have a look under the hood of photogrammetry. And even though I said in the last video that this one will have a lot of mathematics, don't get scared. I will make everything easy to understand and in a reasonable manner. My goal with this series is to make photogrammetry and 3D scanning easier to understand, not harder. And through understanding what actually happens in the background, you can learn some things about how to capture better data, which will give you better results and less headaches. So if you are ready, let's start. With photogrammetry, I mean the process of creating a 3D object from a series of 2D images. Thanks to digital advancements, we don't have to do the conversion, we just have to give our little program the images. Even though there are more steps involved, but let's say it is that easy for this video. So, how does the software create a 3D object from images? Well, there are a lot of concepts involved and the software developers have all their own little secrets to optimization. But that does not concern us, because the most important concepts are nearly the same in all of them. To get you started, let's have a look at which steps are performed to get from image to object. Essentially, and what you will likely see in most software, are at least 3 steps. The first one being camera alignment and sparse point cloud creation, often just called alignment. The second one would be dense point cloud and mesh generation, often called meshing. The last one would be texturing, so your model gets its lifelike appearance. The software starts by aligning the images. This means finding the position of the image in 3D space in reference to the other images around it. To get this done, a process called feature detection is performed on every image. Features are pixels or pixel groups on an image that stick out in contrast to the pixels around them. Basically, an algorithm finds small parts of the image that have a high chance getting recognized in other images. These features are then matched across multiple images. To get more accurate results and prevent false positives, the images sometimes get rotated and scaled by the matching algorithm. After completing this successfully, the software now knows which images are close together and how many pixels difference are between them. Next up is the SFM, or Structure from Motion stage. Here, the 3D camera position is calculated and a sparse point cloud is created. To easily understand how this is done, we can have a look at an example. Let's say we have 2 images, from which we know from the last step that they have matching features. This means they both have some part of the other image in them, often called overlap. We also know the in-strings of the camera for each image, such as focal length, pixel size and lens distortion. They are important because through them we know where the camera is placed in reference to the image. So never remove the lens distortion from your images if you want to use them for photogrammetry. Now draw a line between the center of the 2 cameras. This is our baseline. Next, take a feature that exists in both images, even though we do not know where this feature is in the other image. But we do know this point lies somewhere along a line in the second image. This is the epipolar line. The plane that these 3 points, the 2 camera centers, and the object point form is called the epipolar plane. What we just did is named epipolar geometry, which provides us a way to relate points in one image to lines in the other image, given the baseline between the cameras. Now, we just need to calculate the position of the second camera in relation to the first one. This is done by using essential matrices. These, given a point in one image, give us the corresponding epipolar line in the other image. Through matrix multiplication, we then get the translation and rotation between the 2 camera views. I hope this now sounds easy for you, but in reality the calculations behind these concepts are more complex and involve a deeper understanding of mathematical principles. But for our purpose, this is good enough. This process is then repeated for all images, and in the end, all relative positions are transformed in a common coordinate system. So now we have all cameras aligned. To get a sparse point cloud, we can compute the position of each matched feature pair through triangulation. which involves tracing rays from each camera's position through the corresponding feature point in each image and finding the point in 3D space, where these rays intersect. But because every camera pose is more like an estimation dependent on image quality, we get an error. These errors, or deviations, arise from imprecise feature localization in images, noisy matches and imprecise calibrations. And the error grows with more and more images being processed. But through refinement algorithms such as bundle adjustment, we can minimize the reprojection error, which is the difference between the observed image points and the projected 3D points. We have done it. We now hopefully have aligned cameras and a sparse point cloud. Let's not stop our flow and jump right into how we get our dense point cloud and finally our mesh. To achieve this, we use a process called MVS or multi-view stereo. Because this again is a rather complex process, let's break it down for us. Let's say we try to understand the shape of a statue, but all we have are images of that statue from different angles. That is where multi-view stereo comes in. After structure from motion, we have a rough idea of where our images are in 3D space in relation to the statue. We also have a sparse point cloud of points that generally outline the statue. Multi-view stereo now aims to fill in the gaps and provide more detail. It does this by generating a depth map for each image. A depth map is kind of like a grayscale image where each pixel's brightness corresponds to the distance between the camera and the object at that point. MVS does this by looking at multiple images and comparing the same point seen from different perspectives. It tries to calculate how far that point is from each camera. It is a bit like how our brains use the slightly different views from our two eyes to gauge depth, a process called stereopsis. Once MVS has created depth maps for all images, it combines them into a dense point cloud, which is a more detailed 3D representation of the statue, complete with lots of extra points filling in the gaps left by SFM. Now that we have our dense point cloud, the actual meshing starts. Here, all points in the dense point cloud are connected into a coherent model. Lastly, all images are used to project and stitch a texture on top of the model. And that's it, we did it. We now know how our software creates a 3D model from a series of images. But wait, how does that help us with capturing better data, or images in our case? Well, let's do a quick tour through our new knowledge. In the first step, the software needed to find good and significant features in each image so they can later be matched and grouped. To prevent false positives or no features at all, we need an object that has enough structure. Also, good lighting conditions matter to keep the noise in our images low. Reflective surfaces are also a problem, because shiny spots would not only mess up the texture but would also irritate the software when trying to match images. And even if we could manage to align the cameras, we would still have no features to get good results when calculating the depth maps for each view. Which means even though our cameras are aligned perfectly, the resulting object would be a mess. So both image quality and the object surface structure play an important role. But that is not it. We also learned that overlap is very important for our end result. Having good overlap between the images in all directions makes it easier for the feature matching algorithm to group images together, which in the end results in better camera alignment and object quality. Does that mean more images mean generally better quality of the resulting 3D mesh? Well, unfortunately not really, because the more images you take, the higher is the chance of capturing blurry or shaky images. Plus, more images mean a higher error during structure from motion that needs to be minimized by the refinement algorithm. Obviously, it is better to capture more images than to view, because in the end you should sort out all blurry and too noisy images, and you can still use less in your process afterwards if it gives better results. Now you know what it looks like under the hood of photogrammetry, and if you are interested to dig even deeper into the formulas that hide behind structure from motion or multi-view stereo, you can do so. But after completing the videos I talked about in the first part of the series, it is up to you what topic the videos on this channel will have. So let me know in the comments if an even deeper dive would interest you. That's it. I hope you enjoyed the video, and if so, consider hitting that subscribe and like button.